Fakat tabii yani çok garip. Neyse, seninle ilgili bir şey değil zaten bu. Yani bu derse, Maruf dersinin oral egzamini nasıl koyarlar anlamıyorum ya. Neyse. Peki, şu an derse geçelim de.
Hocam derse başlamadan hemen ben de bir şey sorabilir miyim?
Derse ilgili mi?
Ee, Yani bağlantımla ilgili.
Bağlantılı ders, onları arada sor. Ders bitince, olur
Yani
mu?
internetim gidebilir de hani tekrar girsem sıkıntı olur mu diye soracaktım. Altyapısal bir problem varmış da.
Umarım gitmez, giderse tekrar bağlanmaya çalış, olur mu?
Tamam hocam, teşekkür ederim.
Yani ona benim pek yapacağım bir şey yok. Tekrar bağlanmaya çalış. Öyle ufak tefek aradaki kopmaları zaten asistanlar yok, kabul etmiyor yani, anlatabiliyor muyum? Hızlıca
Tamam,
bağlanabilirsen eğer aradaki kopmaları yapıyor. Devam ediyor, kabul ediyorlar dersi. Çünkü
teşekkür
olabilir.
ederim hocam.
O zaten öyledir. Yoklamalarda bakınca görürsünüz. Şimdi gelelim bu probleme. For the given state of stress, determine the normal and shearing stress exerting on an oblique face of the shaded triangle elements shown. Now, here, there is a cubical element. Somehow you determine the stresses, and we are looking for the stress on that plane, right here. Okay, on this plane. Clear. But the problem says that use a method of analysis based on the equilibrium of that element. The problem is to be solved by equilibrium. Actually, this is not an approach that I prefer, but there are lots of problems in this book. That's why I'm solving this problem. In fact, I'm just going to write the results, not solve the problem totally. Now, if you want to solve that problem, just remove this element and throw it, okay? So when you do it, you have such an element. Say that the directions are correct. Okay, we have such an, sorry, which is geri bir kez daha çizeyim. Say that this is the element that we are referring. Okay. Now, we have already known the following stresses on the element. What are those? We have a shearing stress on this face. Okay. Look at the figure on the left and on this left face, which are equal to 90 megapascals. Okay. So let me write these later. Okay, first let me draw the arrows and then write these. And then we have another stress on this face, which is a normal stress, which are already given in the problem. Now, let us say that we have to attach a coordinate system to talk about stress tensor. Say that this is the x-axis and this is the y-axis, okay? Then if we do that, now you should know this. This is sigma y, okay? That's equal to 60 megapascals as given in this figure. Koordinatsız problem çözülmez arkadaşlar. And this is tau on the x plane in the y direction. Because of symmetry, we are using same subscript for both. And that's equal to 90 megapascals. Okay. And obviously, it is clear that, okay, is this stress is positive or negative? You don't need to show a sign here because you are showing a direction, but is it negative or positive in the equations? Negative, yes. Now, this is the case. We are looking for this. We are looking for the stress on the element. You have to, look, we have to add a coordinate system here. Okay, say this x prime and this as y prime. Now, when you do that, then it's expected you to have a shearing stress on this face. I don't know the direction, but I'm just arbitrarily writing for now. And I have a normal stress. Again, I don't know its direction. I'm arbitrarily putting it for now, which is sigma y prime. That is, we are looking for these two values. Now, you can solve this problem in many ways, in fact, including the Mohr circle. But the problem says that use equilibrium. That's why I'm solving this problem. And I'm just going to write the results. For equilibrium, okay, first of all, look, we have these relations between the areas. So if we say that this is the area A, okay, and then this surface is the area Y, and this surface is the area X. Now these are the relations. Very clear, because we know that this angle here is 30 degrees as given in the figure. So therefore, AY is equal to A times cosine 30, AX is equal to A times sine 30. Now, they are very clear from the figure. What you are going to do is this. You are going to, okay, here are the solution. You are going to first equate the forces in X direction, and then you are going to equate the forces in Y direction. Okay, very simply. Look at this equation. For example, in Y direction, multiply sigma Y prime. Okay. Fontlar küçük geliyor mu bilmiyorum size. İsterseniz biraz büyüteyim, belki daha iyi görürsünüz. 16 yapalım şöyle. Okay. Şunu da 16 yapayım. I'm not sure whether you are clearly seeing it or not. Now look, this is statics. Okay. Now, how you obtain a force if you are using a stress? When you multiply sigma Y prime with the corresponding area, you get a force. Okay, in Y prime direction. So we are looking for the force in Y prime direction. Then on the bottom face, we have sigma Y. Multiply sigma Y, look at here. Multiply sigma Y, okay, with the corresponding area, AY. Now you have a force on the surface. Then take it as component along Y-axis. At the same surface, we have tau xy. Multiply it with AY. Take this component along Y prime. Now look at this surface. On this surface, we have tau xy. Multiply it with corresponding area. Take this component along x-axis. So remember, when we multiply stress with area, we get force. And then we find the components of the force on the respective areas. Now, if you solve this equilibrium equation, you know everything except Y prime, you can easily get the result. Prosedür hakkında bir sorunuz var mı? When you multiply stress with the corresponding area, you get the force. Then find the component of that force in the respective direction. Is this clear? You can do the same thing for the X prime direction. Just write the force balance in the X prime direction, multiplying stresses with the corresponding area, and then if they are not in that direction, find their components from sine or cosine 30 and get this stress, related stress. Very simple. The application is force equilibrium. Now, this is a procedure, but if I were you, I would use not those, but instead these. Why? Because we have already obtained transformation equations for plane stress. This is a plane stress problem, okay? So all the stress are in a plane. You can easily use the transformation equations that we have already obtained. You know the angle, you know all the stresses, just put into these equations, find the same result. This is preferable. And if you have a complicated three-dimensional stress state, it is easier to use these equations, although we have only written to you the two-dimensional equations. I prefer the last, and they are the common approach in mechanics, but you can also use the above two equations by using force equilibrium. Actually, they result with the same stress equations as you see. Any question about this problem? Soru var mı arkadaşlar? Burası statik esasında. Kuvvet, stres çarpı alan kuvveti verdiği için yaptığınız tamamen bir kuvvet balance equation. Oldu mu? There are lots of problems in the book about this, so I just want to solve this problem for that purpose. Okay, now, next title is the stresses in thin-walled pressure vessels. This is the last thing about this chapter. Now, first, let me write this. Pressure vessels. Now, we are talking about thin-walled pressure vessels. Thick-walled will be discussed in ME207, as far as I remember, or ME208, whichever, I don't know, but next year. Now, pressure vessels, okay. Pressure vessels contain fluid, okay, under pressure. Yani evlerdeki örneğin tüpler mesela içinde gaz var değil mi? LPG var. Pressure vessels contain fluid under pressure like boilers, okay? fire extinguishers, you know, these examples, water towers, etc. Now, these are the members contains fluid under pressure. But if the diameter of the or dimensions of the vessel is large when compared with the thickness of the structure that is produced from, then we say that these are thin walled pressure vessels. Okay. Now, since walls of the pressure vessels offer little resistance, since walls of pressure vessels, okay, their walls offer little resistance to bending. Okay, so bending is not a criteria for their design. Okay. Yazayım bunu tamamen. It may be assumed that, of course, this is an assumption. It may be assumed that the internal forces, okay, the stress is a result of those internal forces. The internal forces exerted on a given portion, okay, of the wall are tangent. We assume that, of course, on a small element, to the surface of the vessel. Okay, to the surface of the vessel. Now here, I am going to show you the figure in the book, this one. Now, this is a part of the, okay, this is a part of, let's say, pressure vessel, maybe spherical, okay. And since bending is neglected, all the stresses at the part that you have removed from the body are assumed as tangent to the surface of intersection, okay? We are neglecting the bending effects like beams. That's what I'm saying. Is this clear? So the resulting stress on the element, as a result, the resulting stresses on the element, okay, of wall or on an element, let us say, not on the element, just say that you have taken an element of wall, will thus İlaçlama mı yapıyoruz ya? Kötü bir koku geldi buradan, hep ilaç kokusu. Will thus be contained, okay? So if you take a small element, as you see on the figure, in a plane, tangent, okay, tangent to the surface, of the vessel. Is this clear? So if you take a cubical element on the surface, all the stresses are assumed as tangent. There is no transverse stress, as you see on the figure. As a result, the problem is in plane stress condition. In plane stress condition. Who remembers the plane stress condition? İçinizde hatırlayan var mı? Plane stress önemli bir assumption çünkü. All the stress are, kim hatırlıyor? In a plane, right? For example, this is a plane stress element. Look, if you say XY, all the stress are in the XY plane. We have no stress in the Z direction. If this is the case, if we have no stress in Z direction or in the third direction, let us say, if you have all the stresses in the plane of xy or xz or yz, and if all the loads are in the mid surface, it is called as plane stress. Unutmayın bunu arkadaşlar. Konuştuk. Bütün bu transformasyonlar plane stress transformasyonları. Örneğin şu. This transformation, these two, remember, are for plane stress, these two. Plane stress. Because we are not talking about three-dimensional transformation. We didn't talk about it. Of course, we have corresponding equations, but we didn't. So plane stress means that the stress is in one direction, say Z, sigma Z, tau xz, tau yz are all zero or are assumed as zero. Don't forget. So on the pressure vessels, if we have a cubical element, we are saying that it is in the plane stress condition. Okay, plane stress, because we will talk plane strain later. Okay, if this is clear, if these definitions are clear, this introduction is clear. Now I'm going to start the pressure vessels or derivation of the equations. Now let us start with cylindrical pressure vessels. Okay. Cylindrical pressure vessels. Bunları mutlaka görmüşsünüzdür. Kamyonların arkasında falan. İşte şey taşırlar yani. Basınçlı gaz ya da petrol her neyse. Cylindrical pressure vessels. Now, okay, there is a pressure vessel. Its shape is cylindrical. So what you have actually is this. You have such a pressure vessel, cylindrical, and obviously there is a wall thickness of that, like that, okay? And let us attach a coordinate system, say that this is the z-axis, and here is the y-axis, and this is the x-axis. So this is the z-axis, the axis which is in the along the axis of the cylinder. Now here we are saying that this is the inner radius of the circle. So R is the inner radius of the circle, and this is the thickness of the pressure vessels. Okay, or inner radius of the cylinder and thickness of the pressure vessel. Please be careful. Our book is using R. In our book, R means inner radius of the circle. Now, if you have such a pressure vessel, and if you select such a cubical element on the pressure vessel, such that the sides are parallel to the either transverse section or axis of the circle, such that, then you have two stress on it. One is this and this. The other one is this and this. So look, this is not any cubical element. The sides are either parallel to the axis of the cylinder or parallel to the transverse section. If you do that, this stress is called as sigma longitudinal, and this stress is called as sigma hoop. So this is sigma hoop, this is sigma longitudinal. Okay, there are no shearing stresses in this at this orientation. Obviously, since there are no shearing stresses, both of them are principal stresses. I'm going to turn back later. Buraya kadar bir soru var mı? Tamam mı arkadaşlar? Okay, hoop and longitudinal. So we have sigma H. This is by definition hoop stress. Of course, I'm not talking about stress tensor. Sigma L is the longitudinal stress. First of all, now let's first make these definitions. Now, let's find, of course, there's pressure within that member. Now, let's find the equations for these stresses. For this purpose, consider a section. Consider the following section. The following section. Now, I'm going to take I have taken the figure from the book. Burada bir yerde şekil var mı? Yok. O zaman şuradan alayım, PowerPoint'ten. Kitaptan alalım. Okay. Copy. Paste. Now look, we have taken a section from the book, which is given in our textbook. And if I draw a side view, what we have is this. On the side view, we have such a cylinder. Biraz daha büyük çizeyim. Okay, we have such a cylinder, right? There is a very simple calculation for this. Say that this cylinder. Now, referring to these axes, this is the, say, z-axis, and this is the, say, y-axis. Okay. I'm trying to draw a good view, I couldn't. Anyway, so let me redraw these. Say that this is a cylinder, half of the cylinder that we have seen anyway. Okay. Now look, first of all, if you look at this figure, you will see that there is pressure within the member. And further, these are hoop stresses, okay, as we mentioned, on the thickness. There is pressure within the member, and there are hoop stresses. Now, if we take an infinitesimal area on this member, what we have is this. Now look, let us take an infinitesimal area on the figure on the side. So say that we have such an area, okay, and if you extend the z-axis, now say that this angle is theta. And this angle from here is d theta, right? Is this clear? And then there is pressure with this member. And also we have hoop stresses in this member, sigma hoop, sigma hoop. And because of this pressure, we have such a force acting here. Is this clear? Now look, let's write the force balance in z direction. Sigma Fz is equal to 0. First of all, look at the above figure. We have sigma hoop, right? These stresses are acting on an area which is T times dx. Bakın şu alan arkadaşlar. Okay. T times dx, but there are two of these areas too. Now, this is the hoop stress acting in the positive z direction. This stress is in equilibrium with pressure times this area. Okay, let me show the area here. It is acting on such an area here. What about that area? It is r times cosine, okay. P times cosine theta is the component of the pressure in z direction. We are multiplying it with the area. R times d theta is the arc. This is dx is the length. And if we integrate it from 0 to or minus pi over 2 to pi over 2, then this is the force created by the pressure. Okay. This is dA. This is the component of the pressure along z direction. Simply. Statics, right? Now, if you calculate this, integrate this, etc., you will see that. Okay, let me write. Then 2 times, just a minute. Okay, 2 times sigma hoop T times dx is equal to P times R times dx times sine theta from minus pi over 2 to pi over 2, or that's equal to 2πr dx. From here, you can obtain the hoop stress as, okay, PR times T. Please know this stress by heart. P times R times T. Is this clear? Derivasyonla ilgili herhangi bir sorunuz var mı arkadaşlar? Basit force balance. Okay. Okay. Here is dA, it is equal to R times d theta times dx, which is that. Okay. Okay. Now, this is hoop stress. Let's find the longitudinal stress also. Again, it is very easy. Evet, tabii. Ne görmüştük anlayamadım. Bearing stress, evet. Bu bearing stress değil ama burada basınç var, fluid var. Orada iki yüzey temas halindeydi. Burada basınç iç yüzey temas halinde, kuvvetler şeyde, çeperin içerisinde stresler. Yani basınç fluid'in ya da neyse işte silindirin içine etki ediyor. Ama stresler şeyin içerisinde, ne diyeyim, o wall thickness'ın içerisinde. Anlatabildim mi? Şüphesiz basınç, şuradaki basınç örneğin şurada bir kübik eleman alsaydın şöyle, bu basınç burada, bu P dediğin işte ne olacaktı? Sigma Z eşittir minus P olacaktı. Doğru. Ama burada bizim bulduğumuz hoop stres ve longitudinal stres, thickness'ın içindeki stresler, contact stresler gibi düşünme onları. Anlatabildim mi? Senin söylediğin şurası için doğru. Evet, yüzeyde basınç bir boundary condition olarak stres yaratır. Ama bizim bulduğumuz o değil. Bizim şu anda buluyor olduğumuz hoop stresler, yani malzemenin içindeki stresler. Oldu mu? Okay. Şimdi gelin buraya. Now here, again, we are just writing the force balance right now. The force balance in x direction, look, the force balance in x direction, gene aynı mantıkla. Okay, we are saying that force balance in x direction should be zero. So what are the forces? First of all, we have stresses. Now look, within the member we have pressure. And also on the wall thickness, we have hoop stresses, sigma h, right? All these are hoop stresses. So this is a hoop stress, for example. Okay, this is the hoop stress. So therefore, the hoop değil. Hangisi bu? Longitudinal. Okay, hoop deminkiydi. This is longitudinal stress. Bir saniye, sigma L yani. Okay, now look. When I multiply sigma L with the corresponding area, since wall thickness is small, I can use this. 2 pi t, as if it is a circumference of a circle with a thickness t, because of small area. Of course, you can use pi r square minus pi r e square, but the result does not change significantly. Okay, bir dakika, arı da yazayım şurada. Okay, this is the circumference of the circle. We are multiplying it with thickness as if it were a thin member, like that. Okay, 2 pi r, this is thickness, so you bend it and obtain a circle like that. Okay, that's our assumption. Anyway, then 2 pi rt is equal to, okay, is equal to the pressure. What's the pressure? Now, minus the pressure is acting on a circular area, that is pi r square. We are just taking inner diameter, and that's equal to 0. Now, from here, you can say that sigma L is equal to P r over 2t. Now, look, longitudinal stress is the half of the hoop stress. So, turning back to this figure here, it's very obvious that after these solutions, sigma hoop is the first principal stress, and sigma loop is the second principal stress. Okay, one is maximum, the other one is minimum. These are principal stresses on the cross section, and now we learned that sigma hoop is 2 times sigma L. So tell me, if I have a pressure vessel like that, hani oksijen tüpleri falan sanayide patlar ya, böyle yangın çıkar biliyorsunuz. Bu tüp şöyle mi patlar, böyle mi patlar? Bir gibi mi patlar, iki gibi mi patlar? Ya da neyse yırtılır diyelim. Evet, söyleyin, streslere bakın.
Bir gibi değil mi hocam?
Şimdi şuradaki stres, bakın şuradaki stres sigma longitudinal. Şuradaki stres, yırtılan stres sigma hu. Hangisi geçerli?
2.
2 geçerli değil mi? 2 katı neredeyse. Hiçbir zaman şöyle ayrılmaz. Hep böyle ayrılır. Çünkü buradaki stres diğerinin 2 katı. Oldu mu? Eğer basıncı artıp bir şekilde bunun işte delinmesine, yırtılmasına, hatta genelde tabii patlama şeyden oluyor. Yani gazın sızıp alev almasına oluyor. Yoksa bunun böyle patlaması kendi kendine yırtılma şeklinde olur. O patlama başka bir şey. Her neyse. Bu iki arkadaşlar, şunu ezberlerseniz yerini bulursunuz. Bunu bilin yani. Bu by heart bilin bunu. Şimdi gelelim Mohr circle'a. Using Mohr circle, geçen konuşmuştuk hatırlarsanız. Okay. How do we use the Mohr circle? We have two axes. One is the vertical axis and one is the horizontal axis. We all know that horizontal axis is always sigma. We all know that vertical axis is always the shear axis in the Mohr circle. Now, there are two principal stresses. The first one is sigma 1. Now, here we have sigma L, which is equal to sigma 1. Just half of it is sigma A, excuse me, tam tersini yazdım. Hangisi büyüktü? Hoop stres büyüktü. Silgi gelmiyor. Bir saniye. Tamam. This is hoop stress, which is sigma 1. This is longitudinal stress, which is sigma 2. So, our Mohr circle is this. Clear? This is the Mohr circle. Now, on this Mohr circle, here we have the tau, but this is tau max in plane. So, now referring to this figure, we know that sigma 1 is equal to sigma hoop, and that's equal to P R over T. Sigma 2 is equal to sigma longitudinal, that's equal to P R over 2T. And obviously, tau max is the radius of this circle. So, what is the radius of this circle? Tau max in plane. Söyleyin şekle bakarak lütfen. Then, tau max in plane is equal to, what's the radius of the circle? Sigma 1 minus sigma 2 over 2. So it is equal to, yes, 1 over 2, sigma 1 minus sigma 2. Ya da oradan yazalım. Artık radius'u biliyorsunuz zaten. Söyleyin. Evet arkadaşlar, kim söyleyecek? P R over, yes? 4T, yes, radius of the circle. This is tau max in plane, right? Okay, what about tau max? Now, this is actually 1 over 2. Peki istiyorsanız bir kez daha şöyle yazayım. Formül aklınıza daha iyi kalır. Look, 1 over 2, sigma 1 minus sigma 2, which is equal to P R over 4T. But also, we all know that there is always three principal stresses. So we have one more principal stress here, which is sigma 3, and that's equal to 0 in plane stress problems, which says us that we have two more Mohr circles. One is this, okay, and the other one is this. Although we are not talking about three-dimensional Mohr circle, okay, what we know that there is two more circles which are shown like that. Now, if you refer to this figure, we know that this is, excuse me, buraya nasıl geldi? This is the actual tau max. Sorry. Look, bunu geçen derste en son bunu söylemiştim. Bir daha hatırlatayım size. Bir kalem alamadım. Okay, this is tau max. This is tau max in plane, in the XY plane. But since there is a thickness which we ignored, at an angle to that plane, there is another tau max. This tau max, bunu lütfen iyi bilin, sorarız. This tau max is equal to 1 over 3, sigma 1 minus sigma 3, the maximum value between the principal stresses. And this is equal to P R over 2 T, the radius of the other circle. Anlaşıldı mı arkadaşlar? Herhangi bir sorunuz var mı? Yani plane stress'te bakın şunu unutmayın. Bununla alakalı değil ama eğer plane stress'imiz şöyle çıkmış olsaydı Mohr circle'a göre bakın bunu sileceğim. Şöyle bir sadece hatırlatmak için size. Bunun için geçerli değil. This is not valid for pressure vessels. If we had such a two-dimensional plane stress problem, this is sigma 1, this is sigma 2 say. Now here, ya da kitaptaki gibi yazalım ki şey olsun. This is sigma max, this is sigma min in plane stress. Sigma min. If one is positive and the other one is negative, then this tau max in plane is equal to tau max. Why? Because we have two more circles which their shearing stress are small. Is this clear? So here both principal stress are positive. That's why tau max is different than tau max in plane. Bu da aklınızda kalsın. Neyse, şimdi devam edelim. Buna tekrar dönelim. The second thing about the pressure vessels is the spherical pressure vessels. Okay. This is very simple. Spherical pressure vessels. Bunları da mutlaka görmüşsünüzdür. Ayaklar üzerinde bir sürü yerde durur. İçinde basınçlı gaz olarak. Büyüktür çok. Now look, consider the following pressure vessel. This time, okay, because of Hall symmetry, if you take a cubical element at any orientation, you always have such principal stresses. There are no shearing stress here. Whatever the orientation of this element, there are no principal stresses. You have sigma 1 and sigma 2, and because of symmetry, okay, due to symmetry, sigma 1 is equal to sigma 2. Okay. At any element, at any orientation, whatever the orientation of this element is. Now look, here in this one, in the spherical planes, at any orientation is not correct. If you rotate this element a little, you will have shearing stresses. This case without any shearing stresses for this particular direction, where the sides are either parallel to the axis of the element or transverse plane. But for spherical cases, due to full symmetry, there are no shearing stresses on the element. Okay, then let's find sigma 1 or sigma 2 because they are equal. Okay, by using such a section, the following section, okay, gene kitaptan alayım bu şekilde, kolay olsun. Bir şekilde uğraşmayalım. Copy, paste. Okay, now look, this is the section. Again, R is the inner radius, T is the wall thickness of the material. And then we have pressure within the member. There is pressure within the member. But also, we know that these stresses are, ne diyelim, sigma 1 now. Okay, because they are all same. So, if you again write the force balance in x direction, you get the following. The stress times the area, which is 2 pi r because of small thickness T. Okay, this there. Now this is force. That's equal to pressure times projected area, PR square. And then from here, sigma 1, which is equal to sigma 2, there are no hoop and longitudinal stress right now, is equal to PR over 2T. So in spherical pressure vessels, the stress is equal to the longitudinal stress of the cylindrical system, PR over 2T. Just know this by heart. And then if we show this by using the Morse circle, in the Morse circle, what we have is the following. Okay, now remember, Morse circle has two axes, as we discussed. One is the horizontal axis, sigma. The other one is the vertical axis, tau. Okay, now, say that we have sigma 1. Say that we have sigma 1 here. Okay, this is sigma 1, but we also have sigma 2. They are at the same places. Then, isterseniz biraz daha küçük çizeyim bunu. Okay. Now, say that here we have sigma 1, but it's equal to sigma 2. So both principal stress are equal to each other. This is again a plane stress problem, which means that third principal stress is here and it is equal to 0. Could you tell me, by looking this Morse circle, what is tau max in plane? Who is going to tell me?
0.
0. There is no shearing stress in the plane. So two more circles are here. They coincide with each other and they are point right now. But keep in mind that we always have another more circle. Burada bir tane çünkü ikisi çakıştı ve 0. Then here is the tau max for the whole system. Since we ignore the thickness, now we said that stresses are tangent, but at an angle to that, we have the maximum shearing stress. So obviously, tau max is equal to 1 over 2 sigma 1 minus sigma 3. Sigma 3 is 0. So here, tau max is equal to P R over 4T. Okay. Soru var mı? Herhangi bir soru. Demek ki arkadaşlar, küre şeklindeki pressure vessel'larda hangi yönde olursa olsun tek bir stresiniz var. PR çarpı 2T bölü 2T. Silindirikse eğer o zaman stresler farklı. Bir tanesi hoop stres PR over T. Bir tanesi longitudinal stres PR over 2T. Yani küreyle aynı. Oldu mu? Bu stresleri bilin ve bunlar hep tensile. They are positive. If there is tension. Şöyle düşünün bakın. If you have a pressure vessel, they are tensile. But if you have a pressure vessel, there is a vacuum inside it, then these would be what? Yani işte basınç olmasa da vakum olsa ne olacak bu sefer? Atmosferik basınçtan dolayı bütün bu stresler ne olacak?
Minus.
Minus olacak. Sıkışacak bu sefer. Değil mi? Pompalarda şurada burada hep ne olur? Bu tip basınçlar olur. Bir pompa düşünün mesela. İçinde basınçlı. Bir pompayla en fazla ne kadar derinlikten su çıkarabilirsiniz arkadaşlar? Flüt dersini aldınız mı? Daha. Bir pompanız var diyelim. Kuyudan su çıkaracaksınız. En fazla ne kadar derinlikten çıkarabilirsiniz? Mesela 50 metreden çıkarabilir misiniz? Çok da güçlü motorunuz var. Var mı fikri olan?
Hocam çıkaramıyoruz herhalde böyle sorduğum şey.
Çıkaramazsınız çünkü ne olur? Buharlaşmaya başlar su. Basınç çok düştüğü için. O yüzden 20 küsur metreden sonra çıkaramazsınız. Ne olur? Pompaları kuyunun dibine koyup compression'la çalıştırmanız lazım aşağıya. Şimdi bir örnek çözeceğim. Ondan sonra da bu örneği bitirmez. Ne yapacağız? Biraz plane stress anlatıp öbür chapter'a başlayacağım. Yani sondan bir önceki chapter'ımız zaten çok kısa bir chapter. Buradaki bu programlar yalnız önemli. Bundan sonraki programlar. Çünkü özellikle bundan sonraki problemler diyeyim. Kübik elemanlara geçeceğiz doğrudan bir şekilde. Anyway, now look. At least let me talk about the problem. Now look, a simple problem. We have discussed such a problem previously also. The cylindrical portion of a compressed air tank shown is, there's a compressed air tank. There is pressure within that. It is fabricated from a 8 millimeter thick plate. The wall thickness T is 8 millimeters. It is welded along an helix, forming an angle beta equals to 30 degrees with the horizontal. Very clear from the figure. What we know is that the allowable stress normal to the weld is 75 megapascals. So if this is the permissible stress, we are looking for the largest gauge pressure. I mean, ignoring the atmospheric pressure, their difference. So what we know is this. Look, draw a tangent to the weld. We know the stress perpendicular to that. That's equal to 75 megapascals. What we know is this. Tangent to the weld. Okay. So by knowing this, determine the pressure. This is the question. Okay. Now, remember, all the equations that we obtained for cylinders are for a plane perpendicular to the axis. So if we attach such a coordinate system X and Y, then just take a point on the weld. Let us say this is the point, excuse me, let me show with a different color. This is the point A on the weld, maybe this. This is the point A on the surface. At A, if you take a cubical element, okay, which is this. Look. Now we have taken a cubical element at A. This element is in plane stress condition. So we have x-axis here and y-axis here. So we know that it is in plane stress condition. This is a plane stress element. Okay. Now, Boran, küçük nane, bana stresleri söyleyebilir misin bunun üzerindeki? Aklında kaldığı kadarıyla şu anda anlattıklarımdan. Çok yeni olduğu için kalmamış da olabilir tabii ama yine de bir şeyler söylemeye çalış lütfen. İçinde basınç var. Ne olacak?
Shearing and normal stress.
Basınçla böyle bir eleman alırsam, yani şöyle bir eleman alırsam, burada shearing stres olur mu?
Yes.
Peki. Bir saniye. Şu elemanda shearing stres var mı?
Shouldn't it be parallel to the surface?
Yok değil mi shearing stres?
Yeah.
Ne var? We only have hoop stress and longitudinal stress. We don't have any shearing stress. Because the sides are parallel to the axis. Birçok kez tekrar ettim. As a result, can there be a shearing stress here?
No.
No, we have only normal stresses. Okay, so one is this. Is this hoop or longitudinal?
Hook.
Hoop, yes, this is hoop stress, good. And then we have this stress and this stress, which are sigma
Longitudinal.
and sigma longitudinal. We don't have any shearing stress, but if we had such an orientation instead, then we would have. But we didn't select it. We don't know the equations for this element, so there is no means to use such an element actually. Okay, so look, then look at this element. On this element, as we discussed, the hoop stress, okay, şimdi bunları sileceğim. Sadece göstermek için yazdım. Çünkü tensör olarak yazmak istiyorum. Okay, on this element, we have sigma x and sigma x, and we have sigma y and sigma y. But as just we discussed, sigma x is equal to sigma hoop, referring to our figure, and that's equal to P R over T. Sigma y is equal to sigma longitudinal, and that's equal to PR over 2T. So look, what we know is that we know thickness, we know T, but we don't know pressure. So we have related these to the following values. Now look, I am looking, what I know is that if I rotate this element as much as 30 degrees, okay, when I rotate this element as much as 30 degrees, this is parallel to the weld right now, okay? This is parallel to the weld. I have a different situation. That is this. Now look, we had the following axis initially, referring to our arkadaşlar şu soruyu bitirip böyle ara verelim. En azından bu kısmını. Now I have a new coordinate system, x prime and y prime. Please follow. And I know the situation with respect to xy. Those are sigma x, sigma y. But now, when I rotate like that, I know that I have, for this pressurized vessel, I have this stress, which is sigma y prime. Okay. Compressive or tensile, I don't know, but there must be a normal stress on the surface. And I have another normal stress on the surface, sigma x prime and sigma x prime. Now tell me, on this element, I have no shearing stress. Can I say the same thing for this element? No, I can't. I expect also shearing stresses on this element without knowing their directions. Say these are the correct directions. We are going to calculate them. This is tau x prime, y prime, where this angle here is, beta. Oldu mu arkadaşlar? Bakın, oryantasyonu değiştirdiğim an shearing stresler çıkıyor. Peki, son sorum aradan önce. Do we know any of these stresses from the statement of the problem? Look, the allowable stress normal to the weld is 75 megapascals. Do we know anything? Hangi stresi biliyoruz? Yes, sigma y prime is the stress which is perpendicular to the weld, is equal to 75 megapascals. Buraya kadar bir sorunuz yoksa ara verelim. Sonra devam edelim. Çözebiliriz, evet. Equilibrium'da. Ama çözmeyin. O mekanikte iyi bir yaklaşım değildir. Çünkü komplike şekillerde onlarla uğraşılmaz. Transformasyon teorileri çok daha doğrudur. Tamam.